This video presents our work SNeRV, Spectra-preserving neural representation for video. Implicit neural representation for video employs a neural network to parameterize video signals. Especially for frame-wise representation, the decoder generates each frame from embeddings with an optional encoder. The fitted decoder itself can serve as a proxy for a video and could be applied to video processing tasks such as video compression, interpolation, and in-painting. However, represented video performance is significantly affected by the characteristics of an input video. Also, inherently, the current methods struggle to accurately capture fine spatial details and temporal patterns according to the spectral bias, which is the learning behaviors of a neural network based on neural tangent kernel analysis, that the network tend to learn the low-frequency components more quickly, while the learning of high-frequency components proceeds at a slower rate. We employ a discrete wavelet transform to decompose a video into low-frequency and high-frequency features, thereby preserving their spatial structures and directly addressing the issue in the frequency domain. The video is mostly consisted of low-frequency components which are suitable to be learned by neural networks. Meanwhile, the high-frequency components includes fine textures and have a sparse representations compared to the low-frequency component. In this paper, we propose a spectra-preserving NeRV that enhances the learning of implicit video representations by efficiently processing different frequency components. After generating frame-wise low-frequency embedding with encoder, the decoder reconstructs low-frequency components and restores high-frequency features with the low-frequency ones as prior. This analysis and synthesis scheme allows for a more efficient representation of the high-frequency textures and motions, based upon the stable base provided by the low-frequency contents. The encoder applies two-dimensional discrete wavelet transform to extract low and high-frequency features. Then, encoder embeds only the low-frequency features to save the parameters. The decoder consists of three components, including upsampling blocks, multi-resolution fusion unit, and high-frequency restorer. Firstly, upsampling blocks is used to progressively increase the resolution of the embedding and reconstruct the spectral information of a target time step. Then, the multi-resolution fusion unit fuses features from different resolutions to enrich the low-frequency features. Lastly, the high-frequency restorer restores three high-frequency components from multi-resolution low-frequency features. We extend the backbone to analyze the effect of considering temporal redundancies. We use a backward and a forward set and apply 3D discrete wavelet transform to decompose frequency components along temporal axis. Additional embeddings are generated for each set and are processed with temporally extended upsampling blocks. This operation allows to exploit temporal information in frames, resulting in an enhanced expressive capacity of the network over time. In experiments, SNeRV presents the highest video regression performance among the tested methods. Also, the video interpolation results shows that the temporally extended SNeRV achieves the highest performance among the tested methods. We present the total encoding time per frame along with the regression performance and interpolation performance. In terms of model complexity, our model offers reasonable trade-off compared to the previous methods. We compare video compression results with commercial video codecs and learning-based codecs. Our methods do not apply additional techniques such as quantization-aware training and predictive coding to improve coding efficiency for fair comparisons. Accordingly, we integrate our model into SNeRV's coding framework and show that our method successfully improves the coding gain. Jockey and ready sequences contain fine textures and motions, yielding some high-frequency components that are challenging to represent with an implicit neural network. According to the training rate graph, the low-frequency components are steadily trained to reach the convergence points, producing similar performance compared to the tested methods. However, while the previous methods fail to efficiently learn the high frequency, our methods achieve significantly improved performance with increasing encoding time. These results verify that our model could mitigate the spectral bias and successfully preserve high-frequency components. Thank you for listening. For more details, please check out our paper and code.